In this session, we're going to start with the sequential circuits. In the first part, we will be dealing with the basic storage elements and how to do the sequential circuit analysis. So, the first part deals with the introduction, of course, and the types of sequential circuits. Then you will see some basic storage elements, latches and flip-flops namely, and then we will go ahead and try to understand how to do the sequential circuit analysis, and namely the state tables, state diagrams, and the concept of equivalent states, and Moore and Mealy models for the our analysis on the sequential circuits. Okay. A sequential circuit contains the storage elements, namely these ones, the latches and flip-flops here. They hold your state, okay, state information right here. Okay, this is your state information. Okay, I wrote it very bad, but I mean it. So the other part is the combinational logic, how the system works, and these are your states. So it's a multiple input and multiple output switching function. The inputs are the signals from the outside, and outputs are the signals to the outside, of course. If you put this in a box like this is what you see. Okay. The other inputs to the current state input and next state input are something going inside. Okay, these are the signals from the storage elements, and the remaining outputs are these are the next state, and these are the current state inputs to your system. So your next state function can be a combination of your inputs and current state right here. Okay, your next state will be dependent on your current state and the inputs, of course. Okay, this is what is obvious from this schema here. And if your output function is a Mealy machine, we will discuss this in a few moments. So your outputs will depend on your inputs and your current state, okay, if it's a Mealy machine. But if it is a Moore machine, it depends on strictly on your current state right here. Okay, then it means that you're talking about a Moore machine, and it is a decision that you need to take. So whether you're designing your system in Mealy manner or Moore manner, and it affects the design significantly in the next steps. But we're going to discuss design in the next chapter. Okay. What kind of sequential circuits do we have here? It depends on the times at which the storage elements observe their inputs and the storage elements change their state. Like when do our state update? When do we update our state? That's the idea. If you're talking about a synchronous sequential circuit, the updates are occurring at discrete instances of time. That's the idea. And the storage elements observe their inputs and can change their state only in relation to a timing signal, like such that the clock pulses generated from a clock. You provide a clock to your system, external clock to your system, like a crystal oscillator or something like that. Okay. But if it is an asynchronous sequential circuit, the behavior is, the updates can happen at any time because it is continuous in time when your inputs change. So when your inputs change, your state can be updated. So it's independent of discrete times. We're talking about continuous update here. It can happen anytime, or it can not be updated for a long time, or whatever. If you think about your clock signal as another input to your system, all circuits can be considered as asynchronous in a way. Nevertheless, you can see that synchronous abstraction makes more complex designs tractable. So if your system is updated at discrete times, you can have a more controllable, more understandable, more feasible solution usually. And asynchronous circuits can result in more complex or hard to handle systems, but of course, if you need it, you can rely on them. And the discrete event simulation is we try to understand how our circuit behaves. So here the gates are modeled by an ideal function and fixed gate delay here. Okay, we're just assuming that the gates have a delay like this much of milliseconds or something like this. But your functions are ideal, like we assume that they ideally change at any given time. So any change in input values is evaluated to see if it causes a change in output value. You track it, and the changes in output values are scheduled for after a fixed gate delay when your inputs change. So then after that delay, your outputs, relevant outputs, change with it as well. If you look at an example here, what you see here is a 2-input NAND gate with a half nanosecond delay here. So normally instantaneously it happens, but in fact it takes half nanoseconds to take effect on your output. You can track this from this table here. Suppose that A and B inputs are 1 for a long time. It means that your F instantaneous is 0 and your F output is also 0. And at 0 time, Fi instantaneously changes to 1. Like this is an instantaneous event, like it's happening immediately, okay? Then it means that instantaneously it should go from 0 to 1. But actually it is still 0 until this delay is half nanoseconds has passed. So after half nanoseconds here, then your output really changes to 1. Then at, for example, this particular 0.8 nanoseconds time, again it goes back to 1 here instantaneously. Of course it should go to 0 immediately, but your real output is still waiting for how long? Okay, plus half nanoseconds here, resulting in a real change here at 0.13 nanoseconds here. That's the idea, that's the basic idea about the delays in our sequential circuits. And this is an example, like suppose that our gates have different delays given here respectively, 0.2 nanoseconds for the inverter, 0.4 for the AND gate, and 0.5 for the 0.5 nanoseconds for the OR gate. If you have a circuit like this, it is in fact a simple 2-input multiplexer is what you see here. So your Y input will be either A or B data depending on your selection signal here. Just keep in mind that these should be inverse, like if S is 1, B is selected, okay? If S is 1, B is selected, and if S is 0, then it means that we're selecting A here. That's the idea. And just take a look at this. At this particular moment, as you see, your A and B are both regarding the A and B are both 1 here, so you need to see 1 here no matter which one is selected. But at this time, like this B is selected for a long time here, then okay, this one will be selected, but with a brief delay here, like this is the delay of the inverter here, 0.2 nanoseconds. At this particular moment here, both of them are 0. Both of them are 0 for like, I mean, you have 0 here, but you still have 0 here as well. It's not switching to 1 here. At this time, you see, both of them are 0 for 0.2 nanoseconds, and you see the glitch it is causing for this type of delays. These are usually considered as hazards in your circuit, and you need to take them into consideration in your real life designs as well. As far as I know, they call it hazard-free design, something like this, which are relatively advanced topics for the next parts of this course. Now suppose that you connect this output signal with a feedback path as an input again here. What happens? Now you see that there is 0.9 nanosecond delay here in this path, and what you see here is in fact what is happening here in 0.9 nanoseconds before, right? So your yt is dependent on yt minus 0.9 nanoseconds. That's it. If of course s is 0, if this path is selected, of course. And in this sense, this simple combinational circuit has now become a sequential circuit, just with this feedback path. It helps us to make it a sequential circuit now, because why? Its output is a function of a time sequence of its input signals. And now what you see here is so it's the y is value is stored in these shaded area here. Your y value is taken into consideration. It's like storing your state, okay, remembering it. The simulation example as input signals change with time, and suppose that changes occur every 100 nanoseconds, so that tenths of nanoseconds delays are negligible here. And if you have b equals 1 and s equals 0 here, means that if b equals 1, s equals 0 here, it means that if s is 0, you are in remembering state. It's like turning here. That's it. See, y remembers its previous value. It's remembering, right? Okay. If s is 1 and y is 1, it means that now it is updated with b. Now this b is it's updating. Okay. Now your y is 1, and since s is 0 here, now it is remembering the y output here. Then if your b is 0 again, you don't care, because it is still remembering its value. When your y is b, when your s is 1 here, now your y becomes b, 0. Okay, now this is again an update. Let's mark them. Update. And this is also update. Now again s is 0, and it's remembering that 0 right here. And no matter how much you change b here, it's in remember state and it's still remembering. So y represents the state of the circuit now. It is not just an output as you see here. Normally, if you look at this looks like an output of your circuit, but also its state as well. This is what it tells us. Y represents the state of the circuit. It's not just an output anymore. Now suppose that you place an inverter in the feedback path here. In this path, you place an inverter as well. Now, see, the circuit becomes pretty interesting because it starts oscillating now in the remember state. See, look at this. Like, look at the length of or delay in this path. You see, 1.1 nanoseconds delay in this path, and as long as this select signal is 0, this path will be selected, and now Y remembers A, then it becomes 0. Now it is, for example, 1 here, but you have 0 waiting here, and it will take effect right here. Then it will become 1, it will become 0, it will become 1. You see, it starts oscillating like this. So this is called an oscillator circuit. It can even be used as a crude clock, but you should keep in mind that this is an unstable structure that we have right here. Normally we don't, we try to avoid situations like this because it makes our circuits unstable. Okay, now let's continue with the basic reset not latch. It is created with the interconnection of your NAND gates here. When you cross couple them like this, this output is connected as its input, and this output is connected as its input like this. This gives you the reset not latch. These correspond to, it is activated with 0 signal, active low. It means that when you need to set, you need to provide here 0 signal. When you need to reset here, you need to provide here 0 signal. Now, if you have both of them 1, it means that you're either not setting or not resetting because you don't know anything. But if you reset it, I'm sorry, if you set it here like this, look at this. If you set it here, it is set, Q is set to 1. And if both of them are not as selected, now it's remembering this, then it's remembering. And then if you reset it, look at this, it is reset, it becomes 0. Then it is remembering 0 here. Now this is something pretty interesting. Both of them are active now. You are both setting and resetting, which is a forbidden pattern of inputs here that can cause your circuit to go unstable. This is the problem with reset not latches. If you do this with NOR gates, the same structure with NOR gates, it will give you set reset latch. Not surprisingly, you set with 1, you reset with 1 here, so neither of them is selected here. Now this is in set state, then it is in remember state, remembering this one, then this is in reset state, you see, resets Q to 0, and it is now remembering 0 here. This one is forbidden now because if you set and reset at the same time, it's something like an unstable thing, and then you shouldn't. You should avoid this 1-1 combination here instead of 0-0 here. Again, this one is a forbidden combination. Now, if you add an extra 2 extra NAND gates here at the previous part, you can make it a clocked one. Like if you add a layer of NAND gates here with a clock to your reset not latch, then it becomes a set reset latch, like it holds information. Its behavior is pretty similar to set reset latch, except that S and R inputs are only observed when the clock signal is high. That's it. It's called control or clock signal. what you see here is, okay, you will have set reset 0, it's no change state, see, no change, and this one means clear or reset. You see it is strictly set to 0. This is set state, so it is strictly set to 1, and this one is forbidden. And if you have 0 0 here, no change, and this one is if you have 0 and 1 here, it means that you're resetting the circuit. It's clear again, setting again, no matter what you have here. But this is remembering, and this one is the forbidden pattern again. Okay, that's it about the clocked set reset latch. So if you want to get rid of the indeterminate states here, like or this forbidden combinations here, like 1 1 or 0 0 in the previous latches, D-latch or data latch is introduced here. You just then add an inverter here to the one of the inputs here, and it means that your set and reset cannot be the same signal at the same time, so it becomes your data latch. And this is the graphic symbol for your data latch: data input, clock signal, Q output, and this is the extra Q naught output. It has namely only 3 states here. This is your no change. If your if your Q is 0 and data is 0, it will be. If your data latch is 1, it will be 1. If your data latch is 0, it would be 0. If your data latch is 1, it will be 1. You see, no matter what your previous Q is, it always takes into consideration the value provided right here in data. If it is 0, the output would be, the Q would be 0. That's it. So I think it's pretty straightforward to apply. Now the flip-flops are dealing with the latch timing problem. There are several solutions for this: master-slave flip-flop and edge-triggered flip-flops. Here, let's introduce them. There are delay paths from one storage element to another, and for a clock D-latch, maybe you have noticed the output Q depends on the input D whenever the clock input has value 1 here. As long as the clock input is 1 here, they are allowed to change, which is not very pretty, right? Why? Because if you have a structure like this, suppose that there's a feedback path like this, as long as your clock signal is high and your Y signal is changing fast here, it means that it can change multiple times within a single clock pulse. This behavior is clearly unacceptable. Normally we expect, or we need to have designs like Y changes only once per clock cycle. That's what we do. A solution to this latch timing problem is to break the closed path from this Y to Y here, like this one, this closed path, into with a master slave flip-flop here, like this one. Okay, master and slave. So it means that you're breaking the path here, like this. Set reset master slave flip-flop solution consists of 2 clock SR latches here, as you see in the picture. And see that the clock on the second one is an inverted one. The input is observed by the first latch with clock pulse signal of 1. It means that this data will be transferred to right here. And when your output is changed by the second latch with C0. Now, when your C0 signal comes here, it's waiting here, right here, and they're not allowing it to pass here unless you provide here 0 now. Then it is allowed to pass here, and that's it. So master slave. So it's a 2-stage here. It means that you need your signal to go to 1 and 0 to take the input value, have an effect on the output value. But the thing is, there's still a problem here, and suppose that your Q is 0 and S goes to 1 and then back to 0 with R remaining at 0. It means that the master latch will set to 1 here, right here. The master latch will set to 1 here, and a 1 is transferred to the slave. And suppose your Q is 0 and S goes to 1 and back to 0 here, and reset can goes to 1 and back to 0, then it means that the master latch sets and then resets. It's not a desired behavior, and this time a 0 is transferred to the slave here, right here. So it means that this behavior is not something neat, and it is called once catching problem. In order to solve this, another approach has been implemented, which is called the edge triggering. Instead of making the transitions strictly at the clock signal here, it means that the transfers are allowed during this time. So as you see, this is causing in once catching problem here, provided that this is your clock signal. Instead of this one, you go ahead and try to build a structure where the updates are happening only on positive edges, for example, of this signal. So it means that it can happen instantaneously. So to avoid this once catching problem. So when you replace this SR latch with a D latch here on the first SR latch here, it means that now once catching behavior can be avoided here. In this sense, the output is observed. Look at this one. When S is 1 here, this one will transfer its value here, and when S is 0 here, this one. So look at this one. At this particular falling edge of this clock signal, this particular clock signal here, the transition will occur, and this is called a negative edge. Look at this, it's a negative edge triggered flip-flop. If you want to have a positive edge triggered flip-flop, and if you want your signal to change its values or updates to happen at these times, then you need to have your clock signal input here, and this is our standard choice for flip-flops in most of our sequential circuits, the positive edged D flip-flops. And each of them has symbols, of course. So far, what we have seen so far have different symbols. Let's see them one by one. This is your SR latch. Okay, this is your Q and Q nut outputs right here. This is your S nut R nut latch, and D latch with 1 control, D latch with 0 control. So it means that your updates will happen during these times, right? So with 0 control, but with 1 control, the updates will happen here. And the ones below are the master slave flip-flops with this is positive triggered one, negative triggered one, and this is positive triggered D1, and this is negative triggered D1. These are your master slave structures here, namely this one and this one. Okay, the versions of it. Okay, and finally our edge triggered flip-flops are given at the bottom here. This is the symbol for positive edge triggered D flip-flop and negative edge triggered D flip-flop. Look at this. These are the things that you need to keep in mind here. it means that these are pulse triggered, like at any given time, this one. But if you have this sharp triangles here, it means that they are triggered, and they are edge triggered flip-flops. And if there's an inverter here as well, it means that it's a negative here edge triggered flip-flop as well. That's it. These are the symbols that you can put in your own works or when you're answering your questions in the exam. And what about the direct inputs here? At power up or at reset, all or part of a sequential circuit is usually initialized to a known state before it begins operation. Okay, I have a flip-flop here, but does it start with 0 or does it start with 1? No problem here. You will have here direct inputs like set and reset here. If 0 is applied to reset here, the output, direct input, will give you 0. If 0 is applied to set state here, it means that you're forcing it to start with from a particular state. This is what you need, because when you turn on the circuit, you want it start from either one of them, either from 0 or 1, right? So that you can understand where it goes.